So this is a joint work with Sebastian Erdweg from TU Delft, Oliver Bracevac, Andi Bejleri, and Mira Mezini from TU Darmstadt. So type checking might take considerable time, especially if we consider large code-based programs, which it can contain thousands of classes. So, but actually what we want, it is a faster, for example, faster feedback from IDEs. And imagine if a change, for example, it is considered every keystroke or a name, then we would not want that for a single change to have a retype checking of the whole program. So, therefore, in this work, we consider to have a incremental type checking for object-oriented languages. But actually, it started with investigating and realizing and incremental type checking for PCF and extensions of it as records, system F, or subtyping. And this is a work which was published in Uppsala 2015. So let me just show briefly how we did this and how we realized it. So actually for us, we consider for just the contextual typing judgment for simply type lambda calculus, where an expression E, it is type checked under the given context gamma, and it returns the type T. So the version in our incremental type checking, we call it co-contextual because the expression E, it is type checked without a given context. So instead of the context, we introduce the so-called context requirements. Namely, we demand a given variable to have a certain type, which we know or we might not know. For example, let's just consider a simple type rule, which is the abstraction rule. And in this rule, so because it is type lambda calculus, so X, it is annotated with the type T. It is annotated with type T1, and the expression E, it is type checked under the extended context with this bounded variable X. So the corresponding co-contextual version of this type rule, it is type checking the expression E, which gives a resulting set of requirements. But since in this case we know now the actual type of X, therefore, if X it was part of the requirement set, then we just remove it because it is satisfied. And actually, doing this kind of type checking, it gave us about up to 24 times speed up compared to the usual contextual version. So then we said, yeah, why not? We can just see how it might work for object-oriented languages. And in this paper, we studied Featherweight Java. So first, let me just give an overview how the type checking in Featherweight Java works. So we consider a class declaration list, which has two methods, size and int. And actually, this class declaration with these two methods, I will use throughout the presentation. And what we want to type check, it is this expression, which is a plus operation. And this is the syntax tree from type checking this expression. So as you might know, the context and the class table are propagated from root down to the leaves of the tree. And the same it is done for the right operand. So, but actually, in order to type check and to know the type of add, first we need to know the type of the receiver. So that's why we know that from constructor call list, we just know that the type it is list, and when it is now part of the language, so we know it is an integer. But so to know the type of add, first we have to match the receiver. So we see, actually we have a class declaration list, which has a method add, and also the parameter type, it matches the type of one. So yes, we can look up this method to the class table, and therefore we just return list. The same it is done for method size, where this method, it is looked up in the class table, and it returns an int. The same, it is done for the right operand, and we return these types. And in the end, we suppose we have a typing rule for the plus operator, and it returns an int. So as you can see, context and the class table, they flow top-down, and the types flow bottom-up. So let me now zoom out and consider a large syntax tree for larger programs. Nodes of this syntax tree, it can be class declarations, like for example C, D, N, E, and F. And as I shown previously, these classes can build dependencies between them. And also the class table now it is made up from these class declarations. And as I showed, we need to type check different expressions we need to look up in the class table. Therefore, each of these nodes, it will be dependent from the class table. As you can see here, there are a lot of dependencies built. So actually, what happens in a change, it is done to a single node. So this change, it will be propagated to the class table. And from the class table, then it may affect the whole syntax tree. So we need to retype check the entire nodes. So as you can see, there are built unnecessary dependencies between these nodes, which poses some problems. And this coordination that class table does inhibits compositional type checking and incremental type checking. And in this work, we focus mostly on the incremental type checking. And what is our solution actually to this problem? So our solution is that we propose a co-contextual type checking for Featherweight Java, which type rules are defined without a class table. So just remove entirely the class table. And this enables incremental type checking. So let me just give first a brief overview how the co-contextual type checking works. Again, we consider the syntax tree, and actually now this is a bottom-up technique of type checking. So where the type checking, it starts from the leaves of the tree, and instead of looking up the information in the class table, we introduce the so-called class table requirements. These requirements are a structure that demand classes to have certain members. For example, if we have a method invocation from a class C for a method M, that we demand that class C should have as member this method M. I will show just after 2 slides how these requirements look like. And so yes, we type check every leaf of the syntax tree, and all the requirements are propagated up to the root. But actually now, as we see, dependencies, they were not built, and if a change it happens just at one of the leaves, that this change, it will not affect the entire tree, but only the roots that are immediately connected to this change. And it is propagated up to the root. So as you can see, we do not need to retype check the whole tree, but just in this case, for example, 4 nodes. And for the other nodes, we can just reuse the requirements from before. Now, let me go zoom in again and just show how actually works through a simple example. So this is the operation that we want to type check. It is a concatenation between 2 lists. And again, the syntax tree from type checking this expression. So as I said, we start from the leaves of the tree, where we type check first the constructor call. We know that it is a class list, so we just return list. And now the requirement for a constructor call, it looks like this. So we assign a constructor signature, which we call it init. And in this case, since there are no parameters from the constructor call, so therefore also the signature, it will be empty, so it has no parameters. For 1, we return it as a number, so we just return int. And in this case, we now need the type for add. But as I mentioned, we have no class table, so we cannot look up this information, return the type of add. So what do? We introduce a fresh class variable, which we call it u1, and correspondingly generate a new requirement for this node. So the requirement, it looks like this. So we ask and we demand, we require that class list has a method add which has just a single parameter of type int, and an unknown return type, which we might learn it later. So the same it is done for the right operand, where we again introduce a requirement for the constructor call and again for add. As you can see here, we generate another fresh class variable, because since no context it is shared between the nodes, therefore for every occurrence, regardless it is the same method, we introduce a fresh class variable. In this case, we call it u2. And all these requirements, they will be propagated up to the node. So as I shown, types and requirements, they're all propagated up. But as you can see here, we have 2 requirements that have the same receiver and the same method name, add. So what should we do? Can we merge them? I mean, why not? Because it is the requirement on the same methods and have same receivers. So what we propose is that actually, since receivers are the same, a class can have only one method, which, for example, in this case, add, and has the same signature. So it cannot have the two methods with the same name but different signatures. So in this case, we just keep one requirement and instead introduce a constraint stating that since it is the same method, then the return types it should be the same. So U1 it is equal to U2. So far, I just shown you briefly how actually co-contextual type checking works. But things get more complicated if we consider features of Featherweight Java. And in the paper, we address these three challenges, which are nominal typing, inheritance, and subtype polymorphism. In this talk, I will just show nominal typing. And regarding inheritance and subtype polymorphism, you can refer to the paper for more details. The expression we considered before, it was this one, and now we add one more method invocation, which is regarding method size. Again, this is now for simplicity, we start first with the just left operand. So this is the syntax tree from type checking the left operand. And as I said before, type checking, it starts from the leaves, generating requirements. So far, so good. We have seen this. But actually, now we have to type check size. Again, we cannot look it up in the class table. Therefore, we generate again a new class variable U2. But in this case, as you can see here, the receiver for size, it is unknown. So actually, operations then on this requirement, it will be more difficult because this requirement where the receiver, it is unknown, it is related to the nominal typing feature. So now we do the same for the right operand, type checking, and generating requirements. Again, for size in this case, it has an unknown receiver. So these are the entire requirements generated from type checking both operands. And so now let us look closely and see these requirements if we can merge them or not. So as you can see, we have two requirements regarding add and two requirements regarding size. First, let us consider requirements regarding size. So since the receiver, it is unknown, actually, so what should we do? Can we merge them or not? It is undecidable, so we don't know. Therefore, we distinguish two cases, where receivers are the same and when they are not the same. So when they are the same, yes, then merging is possible. So therefore, we state that, okay, since merging is possible, we keep only one requirement and the return types, it should be the same. If receivers, they are not the same, that merging, it cannot be applied. Therefore, we just keep both requirements. And actually here it is shown just as conditions, and in the paper, we call them conditional class requirements, and the constraint generated here, it is called the conditional constraint, because it depends on these two conditions. Now, let us look to the two other requirements regarding add. Again, we distinguish two cases, but actually in this case, it is much simpler because, as I shown before, so now the receivers are known. So therefore, we can just say that, since the receiver now are known, we actually know that the return types are the same. So U1, it is equal to U3. And the other condition where list, it is not equal to list, it is not true. So we just do not need to generate any more requirements. So since we learned this piece of information that actually U1 it is equal to U3, now we can reconsider, just go back now a step and see again the requirements regarding size. From learning that U1 it is equal to U3, then we know that this condition does not hold anymore, so we can discard these requirements from the requirement set. So to conclude, the resulting set from merging, it will be just these three requirements and two constraints. So far, we have seen how we type check expressions. This was the resulting set of requirements from merging. But now, what do we do with these requirements? How we satisfy actually them? And the satisfaction, it is realized when we learn information for the classes. So when we type check class declarations and method declarations. So let me now consider again this syntax tree. And as before, we generated all these requirements. So now we learn the information, we are type checking the class declaration list, which has these two methods. So first consider the class header. And this it corresponds then also, we see that it does not have any constructor, so the constructor it is default, it has no parameters. Then this requirement regarding the constructor signature, it is satisfied because it has no parameters, and this signature it has no parameters, done. Now it remains only two requirements to be considered. Let us look closely to these two. We consider now the method declaration size. And as you can, we can observe that, yeah, actually it corresponds a requirement regarding size. But actually we do not know if we can satisfy this requirement or not, because of nominal typing now we don't know the receiver, so what should we do, satisfy it or not? We now distinguish two cases. So if you want, actually, we will learn later that it is equal to list, we just generate, actually now we can resolve the return type, at this requirement it will be satisfied. If you want it is not equal to list, it means that it just happens that another class, which is not list, it has the same method size. Therefore, this requirement, it will not be satisfied, so we keep it. Now we consider the next method declaration, which is regarding ed. And we see again that it has a class requirement which corresponds to this method declaration. So we distinguish two cases, but this is simple because this is easier from what I shown before. We know the receiver in this case. So since the receiver is known, we can actually resolve the actual return type. So we say that, actually now this requirement, it will be satisfied, and the return type, it is list. So it is just removed from the set. Again, we go back now to the size because we learned this information that U1 it is equal to list. So therefore, the first condition on the left-hand side now it holds. So for this requirement also it will be satisfied, and we know that U2 it is equal to int, and the other requirement it is just discarded. So the goal is that in the end all set of requirements it should be empty. So now from type checking the class declaration with these two methods, we deduce that, okay, the requirement set, it is empty, and actually we can resolve the type variables to their actual type, so there are no more left unresolved. Therefore, the program, it will be well typed. So now let me go back to incrementalization and how we did it, because this was just the technique how it is co-contextual type checking, so why this enables incrementalization. So to do incrementalization, we use memoization as technique, and also to obtain a faster feedbacks, we are doing some optimizations, which is condition normalization, in-depth merging of conditional class requirements, incremental and continuous constraint solving, and this is also enabled from what I shown you before, from having a merging operation, and also tree balancing. We also did a performance evaluation where we first measured the initial run and then the incremental run after a certain change happens. And we conducted this evaluation or synthesized Featherweight Java programs and on real Java programs. First, let me show the results for synthesized Featherweight Java programs, where we synthesized about 1,243 classes. And all the initial, the co-contextual, and these are the results. The initial and co-contextual run are compared against Java C. And actually the initial run, as expected, it is 38 times slower than Java C, but actually the incremental run, it is 5.6 times faster. So for these were the results, just the most representative one, because actually we have a larger set of evaluation. Now for the realistic Java program, we used functional data structures like trees, and we used the Belen trees and Erdweg trees, which are about 500 lines of code. And these were the results. Again, the initial run, it is slower, 3.2 times slower, and faster by 1.6 times. Since you can see here results, it is a bit not that much faster than Java C, because actually we needed to write ourselves some code on Java which only represents the whole features of Featherweight Java, and then translate this code to Featherweight Java, because outside we couldn't find large projects on Featherweight Java. So that's why this is not representative for larger projects, for large-scale programs, but we hope that it will scale and we will get faster speed-ups. So also, now in the paper, we have detailed typing rules for, sorry. So we have a detailed type rules for expression, method declaration, class declaration, and programs. And also, the most important, we have a detailed proof of equivalence between these two systems. So actually, if an expression or method it is type-checked in the Featherweight Java, it is also type-checked in Co-contextual Featherweight Java, and the result it will be the same. So we prove equivalence between two systems. We give also a detailed explanation for the optimizations that we did, and also you can see also the whole performance evaluation. So to conclude, we defined a new way of type checking where type rules are defined without a class table, and this enabled incremental type checking. We also addressed the challenges of nominal typing, inheritance, and subtype polymorphism. On the ongoing work, we want to go towards full Java and to see actually if it scales for full Java. And we will consider the features like generics, method overloading, or also wildcards, because it is a paper for wildcards which is added on top of Featherweight Java, generic Featherweight Java. So once we have generics, maybe we can also consider that. So thank you for your attention. If you have questions.
Thanks for the talk. As you compare your approach to Java C, I was wondering if you have started or planned comparing it also to the Eclipse Java compiler, which is already optimized towards incremental compilation, which Java C does not consider at all. So inside an IDE, there is other tricks to speed up incremental compilation. Is that in the scope of your research?
No, actually we didn't conduct run on the incremental, but so the idea how to gain this incremental type checking, it was that we can do it in a systematic way. But because we actually wanted to see how in Eclipse IDE incremental type checking works, but for that it didn't have that much information, and we are not sure actually if this idea can be applied systematically to other systems. But for us, we use a systematic idea, so that's why we started first with PCF and then apply it to object-oriented languages, so in this case to Featherweight Java. But no, we didn't try, we just compared with Java C.
That was the second question. Yeah.
Hi. I'm a little bit worried about method overloading. Yes. I mean, it is sort of a theme for today, I suppose. It just makes everything terrible. I mean, do you know? I mean, is there anything you can even say anymore about if two methods could have different same name but different signatures? Seems like the name is sort of crucial. I don't know.
Yeah. So actually, I do not expect that the translation would be that easy, because considering method overloading, yeah, it is not easy feature. But so I have a feeling that yes, it is possible to do method overloading, but it would not be an easy translation from contextual to the co-contextual version. Yeah.
Here's another question in the front.
So it's very tempting to have a clean bottom-up method for this. However, as we have also learned from previous presentations, programming languages not only have types, they also use types, and so do language processors, right? So once you've synthesized types, you usually want to keep them in the nodes, or somehow have ways inside the node to know its type. Right, so once you've done this thing going bottom up, and once you've done all the unification, you resolved everything. You know what U1, U2 corresponds to. You usually would need to propagate it back downwards.
No.
So have you considered that in the measurements, and also how does that correspond to, you know, because everything will become yellowish in that sense?
No, we don't need to propagate everything against downwards because, I mean, all information that we need to resolve these constraints, it is at the root node. That's why we were propagating also with the types, and requirements are all propagated up. So we don't need to propagate anything again down. So after merging, that's why we did this merging of requirements.
Yeah, theoretically you don't have to, but if you have a compiler that kind of needs to ask for a type of the same node several times for optimizations for different things, wouldn't you want to cache it?
Yeah, we do memoization. So for incremental, we use memoization as technique.
Right.
So yes, it will be cached.
And that was included in the measurements?
Yes, exactly. Yeah, that's why we had two numbers, which was the initial run and then the incremental run after a change happened.
Okay, any other questions from the audience? If not, then I have plenty of time. No, I have one question actually. So, what are your ideas to evaluate this for, let's say hypothetically, in a few months you have larger language support, like Java with generics and things like that. How would you evaluate the incremental changes so that they're you know, realistic for how people develop programs?
Yeah, so for the incremental, so what we did so far, we had, for the incremental change, we encountered 3 natural number classes, and all the other nodes of the program depend on these classes. So actually, if you change one of these nodes, then it will depend all the others. So we think that it was a nice use case, and still we had faster speed-ups. So the change that we do, it will be just for classes that actually all the other nodes can be dependent on these.
Okay, so it's kind of like a worst case analysis. So great. Okay. Well, thanks a lot. And I think we have to switch over.